loud is being recorded. Thank you for saying that. So benzylic halogenation is one that you learned back in radical reactions in OCHEM 1. So if you don't remember it, that's not a huge deal. You're getting a quick review right now. We're not going to go through the mechanism of radical halogenation, but do know that multiple halogenations are possible. So if you're not controlling it with, something like one equivalent, it's very likely that you're going to end up with multiple halogenations. Another way to do it with quite a bit more control is to use N-bromosuccinimide. This is another thing that you learned about in OCHEM 1. So N-bromosuccinimide, or NBS, can be used with either an alkyl peroxide or just a regular peroxide or light. And you can put on just one substitution in the benzylic position. So remember, the benzylic position is just this carbon that's directly attached to benzene. So if we have a longer carbon chain, the substitution would still happen in the benzylic position only.
Sorry to interrupt you. I'm so sorry. I wanted to know, were you going to post the PowerPoint for this chapter? It's a little bit harder to follow.
Okay, I thought I did, but if I didn't, I will fix that after class.
Okay, thank you.
Okay.
Oh, thank you.
Okay, so yeah, N-bromosuccinimide is a way to do a more controlled halogenation at the benzylic position. The reason that this is valuable is that you can then do substitution reactions at the benzylic position. So if we put in a single bromine, we can react with sodium ethoxide and do an SN2 reaction, kick out the bromide, and end up creating an ether. Right? You could do that with any nucleophile, but this is just an example. That's what makes this particularly useful. The next thing that you want to consider is that any eliminations that you do in the presence of a benzene ring are going to favor the conjugated product. So conjugated, again, this is a term that we learned earlier on in the semester. It means that you have unhybridized p orbital overlap. So we're talking about having a double bond in between the benzylic position and the carbon one removed from benzene. Versus something like this, where the double bond is isolated and not in conjugation with the benzene ring. So if you have an alcohol substituting the position one removed from the benzylic position, and you heat it up in the presence of an acid and heat, a concentrated acid, no water present, you would end up favoring the conjugated product. So for example, if you had a halogen and you added in a base in order to do an E2 elimination, it would favor the conjugated product over the isolated product. There are other factors here as well, such as this one is also the more substituted alkene, so that's going to be favored as well. But this also means that if you use a bulkier base, it's likely that you would still end up with the conjugated product. I don't tend to make you consider those things though. Okay, so the next thing that we have to consider is the addition to the carbon-carbon double bond of alkenyl benzenes. And again, we're going to be concerned with alkenes that are between the benzylic position and one removed from the benzene. So a conjugated system, right? What you don't need to worry about is something like 1,4 addition. You're not going to have a 1,4 addition where we protonate here and halogenate here, right? We're not going to break the aromaticity of the benzene ring. So if you, oops. Sorry, I didn't realize I didn't draw the products on here. So if you react with just HBr, which product do we expect? I'm going to draw two possible products here. I'm going to give you about 30 seconds. Think about the mechanism of this reaction and determine which product is going to be favored. We'll call this product A versus product B. Also, if you have my like written out notes from my class from when I taught this in person, please note that I flipped these two reactions. So I'm seeing a lot of votes for B. I'm wondering if you're looking at my old notes. So our preferred product is going to be A. Does anybody know why? What is the first step of this reaction?
The double bond gets protonated.
Right. So the double bond is going to pick up a proton. And where do we want to put the hydrogen? Do we want to put it in the benzylic position or the carbon further from benzene?
The carbon further from benzene.
Right. Why do we want to put the hydrogen here?
So it leaves the benzylic position available for the bromine.
Sorry, I'm having a hard time hearing. My sound is turned all the way up, but I still can't hear most of you guys.
So it leaves the benzylic position available for the bromine?
Yes, so we end up with the carbocation in the benzylic position, and that carbocation is more stable than the one that leads to product B because it is benzylic. So this is the carbocation that leads to product B. So we're going to go with product A because it goes through the benzylic carbocation. Okay, so then our other reaction has peroxides present, which tells us this is a radical reaction. So it's going to go the opposite of our regular Markovnikov reaction. Remember, Markovnikov favors the more stable carbocation. This one is going to go through a radical reaction. And so we want to end up with the benzylic radical as an intermediate. So think for a second about how that happens. Remember, the initiation reaction is going to happen between the peroxide and the HBr, and we're going to create bromine radical. Bromine radical is going to react with the alkene, and it's going to create a bond on the second carbon, whereas we put a radical electron onto the benzylic position. So we end up with our bond to bromine and a benzylic radical. And then we terminate with hydrogen later. But this is the important intermediate. So This next reaction is really, really cool. This is just another oxidation, but in all of your previous oxidation reactions, you had to have an oxygen present. So we would take, a primary alcohol and react it with a strong oxidant, such as potassium permanganate. And we would get a carboxylic acid. But we had to have an oxygen on that carbon already. And what else did we have to have on this carbon? Yeah, Isaiah got it. There has to be a hydrogen. So the same rule applies here, but notice there are no oxygens on toluene, right? And yet we react with potassium permanganate and we end up with benzoic acid. There's some really weird chemistry that's going to happen here. As long as there is a hydrogen present in the benzylic position, when you react with potassium permanganate, hydroxide and heat and follow with H3O+, you will make benzoic acid. You're going to obliterate any other carbons that are there. So this next compound, we have one hydrogen. We are able to make benzoic acid. And notice I'm not drawing any other products. We don't care what happens to these other carbons. Now this compound does not have a hydrogen present. Is this going to react in an oxidation reaction?
No.
No. Right, so no reaction. So as long as there is a hydrogen present, you will get benzoic acid. So that also means that if you have a benzene, this is getting crazy. I know I'm not, being overly careful. It does not matter how crazy this is. As long as there is one hydrogen here, this piece will get turned into benzoic acid. So it does not matter how crazy it was. Okay. Are there any questions about this? And I'm never going to want to know what came from the rest of it. Just ignore all the rest of it. Devin asked, so it will cleave everything else off? Yes. Cleave is exactly the word that you want to use there. Okay, so this has some really, really interesting implications here. When you have an alkene, we still have this hydrogen. It turns out it's not actually the hydrogen that matters here. This is more of a cleavage of a double bond. So remember at one point you guys learned about cleaving a double bond using ozonolysis, or we also did it with potassium permanganate. I believe that was at the end of OChem 1. This is more that process. So is there a hydrogen here?
No.
No, doesn't matter. We have a double, or we have a triple bond. We have some pi bonds there. It's going to go through the cleavage process. Is there a hydrogen here?
No.
No, doesn't matter though. So the hydrogen question is about when we have alkyl groups. So if you have an alkyl group, or even something like this, as long as you have a hydrogen here, you will make benzoic acid. If you have a pi bond attached to the benzylic carbon, you will still make benzoic acid. Isn't this the best reaction that you've learned, right? There's only one possible outcome, and you only have to know like 2 rules, right? Is there a hydrogen, or is there a pi bond attached to the carbonyl? Or not carbonyl, the benzylic carbon. So pretty great. There's another way you can do this. You can also do it with ozone. You don't see this one as often, but ozone, acetic acid, and followed by peroxide. You can do kind of a similar thing. Notice that there's a different structure here though. Instead of benzoic acid, we are keeping the R group. So we don't see this one nearly as often. So for example, what compound are we going to get from this reaction?
It would be a carboxylic acid on a butane.
Right. So we would end up with butanoic acid. And notice I'm not drawing anything with the benzene. When you do these reactions, you're doing them to get a certain outcome. In this particular case, it would be to turn the R group into a carboxylic acid. Okay, so kind of weird structures there, or weird reactions. The next thing I want to go to, we're going to skip these slides and we can come back to them, but what I want to talk about for the rest of class, if it takes that long, I should have just exited out of here, is nucleophilic aromatic substitution. So everything that we've done so far with reactions of benzene, other than the side chain reactions we just did, were electrophilic aromatic substitution. Our next big topic is nucleophilic aromatic substitution. So this has a different name. This part is the same, but we've changed electrophilic and turned it into nucleophilic. So in electrophilic aromatic substitution, we created an electrophile, and then benzene, the pi bonds in benzene, acted as the nucleophile. In nucleophilic aromatic substitution, we have the kind of opposite situation. We have a nucleophile that is actually going to attack benzene. Are we able to do an SN2 reaction on benzene? Have we seen that before?
No.
No. So it's not exactly an SN2 reaction that we're doing. This is going to be a little different. So the shorthand for nucleophilic aromatic substitution, usually I use NAS because it mirrors EAS, the name for electrophilic aromatic substitution, but sometimes people call it SNAR so that it mirrors SN1 and SN2. But both of these shorthands mean the same thing. You're talking about nucleophilic aromatic substitution. So nucleophilic aromatic substitution is a little more complex than we would want it to be. What we would want is to have a halogen on a benzene, react it with something nucleophilic, and just trade out the chlorine. But it doesn't work that easily. In a situation like this, no reaction would occur. So in order to get this reaction to occur, you have to have some electron withdrawing groups present on the benzene ring. And the reason why is that we want there to be less electron density at the halogen carbon so that it is more susceptible to substitution. Basically, if electron withdrawing groups are present, that makes this more electrophilic. Otherwise, the electron density is just too much at the carbon where we are hoping to do the substitution. So if we have a single nitro group present, we can do the substitution. Notice that we have to heat it up to 130 degrees in order to get this to work. And if you have my old notes, you'll see that there is a mistake in this answer. So make sure that you fix those. So we are going to sub out the chlorine for a hydroxyl group. So here is our nucleophile. It's not exactly that mechanism though. So notice that we have to have basic conditions here. And then we follow it up with H3O plus so that we can protonate this. If we have 2 nitro groups on there, we have more electron withdrawing groups, and so that makes this even more electrophilic. And so this reaction is going to happen more easily. It's going to happen at 100 degrees. So we have our nitro group, hydroxyl. If we have 3 nitro groups present, this will happen at 35 degrees. We're almost at room temperature. Okay, does this make sense so far? Okay, we're going to take a look at the mechanism now. The mechanism for this is kind of bizarre. It's not just a direct substitution, the way that I kind of doodled it out real fast. It's actually what's called an addition elimination. Whoops, sorry, I thought I drew it out, but I guess I didn't. So in this reaction, what happens is your hydroxide is going to attack at the carbon where the halogen is, and the pi electrons get pushed over to the neighboring carbon. So we have this intermediate, which has a fancy name. It's the Meisenheimer intermediate. So the reason that this intermediate is important and has a special name is that the resonance forms are actually one of the ways that you can see why this reaction occurs. So you can push the electron density around the benzene ring, just like we saw with electrophilic aromatic substitution. Remember that the structure of the nitro group is really, really important here. There's a positive charge on the nitrogen, which is why we're able to stabilize this intermediate with a negative charge there. You can also push these electrons down into the nitro group, which is one of the ways that having the nitro group present makes a big difference in this reaction. So we've pushed all the electron density into the oxygens. All right, this is really messy right here. And then we can push the electron density back up into the benzene ring. And if you're having a hard time keeping up with these structures, there is a lecture that I'm going to post where I cover the exact same thing. Okay, so those are all of our intermediates. So they're all resonance forms. The next step of this reaction is the elimination part. So we did the addition, the hydroxide added to the benzene ring at the halogen carbon. The next part is the elimination. So these electrons here are going to form a double bond and kick out chlorine. So that is the elimination portion of this mechanism. Does this make sense so far? Are there any questions? Okay, so obviously I can't ask you to draw out this mechanism on an exam, but what I can do is ask you questions about the mechanism, or ask you to identify, the type of mechanism, or give you several drawn out mechanisms and ask you to identify the correct one. So I do want you to understand how this works. The next situation is that you can do nucleophilic aromatic substitution with the azonide anion. So azonide we've seen before. Usually we see it as sodium azonide, but it doesn't matter what the counter ion is. It's still going to be NH2 minus. Now this one has an even weirder mechanism. Sorry, I can't remember how I did this. Okay, yeah. So this mechanism does not go through addition elimination. It goes through what's called an elimination addition reaction. And because of that, the products are a little less obvious. So if you just have something like bromine present, this reaction actually happens pretty readily. Azonide is a pretty strong nucleophile. Look at this temperature that we can do this at. We actually have to cool it down to keep this from going too crazy. And you're going to end up with a direct substitution of that bromine, or at least that's how it appears. But when we look at the mechanism is quite a bit trickier. So let me see if I drew this out. Nope. Okay. So in this mechanism, I did not do myself any favors in the way that I drew this out. I want the double bonds in a different position. Just because it's easier. So this mechanism does something really bizarre. It's an elimination addition, which means that the elimination occurs first. So we are going to create another pi bond on something that is already aromatic. And we're not going to do it by creating some pi bond here. We can't do that because that would end up having 5 bonds to this carbon. It would be a true mess. You're not going to be able to eliminate a hydrogen atom. But what we can do is pull off this hydrogen, create a triple bond, and kick out bromine. Actually, we're not going to do this all in one step. We're going to do it in 2 steps. So we can pull off that hydrogen, create the triple bond, and kick out bromine. And this gives us an intermediate called benzene. Now, I just want to ask a question. Do you think that benzene, which has a triple bond that has to have this kind of bent cis shape, do you think this is a stable molecule?
No.
Not particularly.
Yeah, no, it is highly unstable, right? Triple bonds want to be linear, and instead we are forcing it to be in essentially at an sp2 angle, right? That is not going to be okay. This is going to be highly unstable. And highly reactive. Okay. So what happens next is typically you have an excess of NH2. It's going to attack, put the electrons back down. And then you pick up a hydrogen from an equivalent of ammonia, which you made up here. Sometimes this reaction is done in the presence of excess ammonia. And then that gives you your substituted product, which in this case would be aniline. So the question here is, how do we know that benzene is actually formed? Because this looks completely insane, right? This doesn't look like this should be how this goes. But if you do the correct experiments, you can actually prove that benzene does form. So one of the experiments that was done that proves this, and again, I did the same thing. I used the default benzene and did not correct my double bonds. So if you label a molecule by inserting a carbon-13 atom, so that atom with the star there is carbon-13, you can actually track it using carbon-13 NMR. So we know that the carbon-13 atom in this benzene ring is the one that is that has the chlorine on it. And we react with potassium azonide, and we go through benzene. Benzene is unlikely to be collected, like you're not going to be able to stop the reaction and say, ah, I have benzene. It's going to continue to react. So you react it with more potassium azonide in the presence of ammonia. And there are two possible outcomes here. You could end up with the amine group on the tagged carbon, or the amine group could end up on the other carbon. So remember, at that intermediate of benzene, it does not matter which carbon is attacked by the azonide anion. And what we end up seeing is that if you were to do this experiment, you would get 50% aniline with the amine group on the tagged carbon and 50% on the other carbon. So the reason this matters is not because like I want you guys to be, so obsessed with this mechanism. The reason it matters is that sometimes the product is not a direct substitution. So if you have something like this, CF3 is an electron withdrawing group. You see that a lot with nucleophilic aromatic substitution. What we would expect is that the chlorine would be directly replaced with the amine group. But when you do this reaction, the only product that you get is actually the meta product. So this is one of those tricky bits of proof. The only way that this could happen would be if this mechanism did truly go through benzene as the intermediate. Okay, does this make sense? Now, the two reactions that we've looked at so far, we have hydroxide and we have reaction with azonide. They have two completely different mechanisms. Reaction with hydroxide is a direct substitution. It just happens to be an addition elimination. Azonide, however, being a much, much stronger base, goes through the elimination addition reaction, and that's why it tends to have this kind of mess of a product instead. So you have to keep that straight in your head. Now, the last thing that I want to show you is if you were to react benzene with a diene, you can actually get a Diels-Alder addition. And so one of the bits of proof that benzene is formed in this reaction is that if you add in something like furan in at the same time as azonide, you would actually see some of the Diels-Alder adduct. Okay, are there any questions about this so far? Okay, we only have one other topic in this chapter. It's some reduction reactions of aromatic compounds. The bit that I kind of skipped over was some trickier things about dye substitution, which I think we addressed in a Friday problem solving session. So I don't think you really missed too much material. Yeah, we definitely did these in a Friday session. So anyway, this will cover the rest of our material. So we have very simple reduction reactions here. This top one is just showing that if you were to add in your generic hydrogen gas and transition metal, you could very, very, very slowly hydrogenate one of the alkenes. And because of the mechanism of this and resonance forms, it's possible that you could end up with the 1,4 diene, or you could end up with the 1,3 diene. So you're going to get a mix of products here. If you add in another equivalent of hydrogen gas and a transition metal, such as nickel, you're going to very, very quickly get down to cyclohexene, and then one more equivalent of hydrogen gas and nickel, and you end up with cyclohexane. So notice it's only the reduction of benzene, the hydrogenation of a single alkene and benzene, that's going to be very slow. Once you get to something that's not aromatic, the reaction picks up rapidly. There's another type of reduction that's really interesting. It uses sodium metal, ammonia, and ethanol. Or you can use lithium metal instead. This is called the Birch reduction, and if you react benzene with either sodium or lithium in the presence of concentrated ammonia, that's what this liquid means here, is that it's concentrated, you're going to end up with strictly the 1,4 product, not the 1,3. If you do this with anisole, you end up with some really, really interesting results here. You still end up with the 1,4 product, but note that the position with relevance to the methoxy group is important here. It's still going to be on one of the alkenes. You're not going to end up with like the methoxy group here in reference to the alkenes. And then if you work this up with water, in aqueous acid, some really wild stuff happens. So this is typically a single question on a quiz and a single question on an exam. This one you see a lot more often.
So it would be something like you would show the benzene and the Na, NH3, ETOH, and ask us which of the following would be the product.
Mm-hmm. Yeah,
okay.
Or to provide the name of the product for this one. I mean, you could name this as well. So yeah, you could also see it written out in one step. So anisole, or not one step, but one arrow. To get to here. So this is kind of your like token freebie problem. If you remember this, you have one question that you can get every time. So you're welcome to flashcard the Birch reduction. So in the last 4 minutes, I just want to talk to you about what you need to be working on this week. So by the end of this week, we'll be completely done with chapter 15. We are going to do chapter 15 problems. We're going to review just all of chapter 15 on Friday. So you'll see nucleophilic aromatic substitution in our problem session. You'll see electrophilic aromatic substitution. You'll see some more complex electrophilic aromatic substitution, So you definitely want to be prepared for Friday's class. You're also going to see a lot of problems that mix several chapters, just like you saw a little bit of on your quizzes and exams. So we're going to work on multi-step problems on Friday. And then this week, you're also going to see Chapter 16 lectures appearing in addition to the rest of Chapter 15. So definitely start reading Chapter 16 through the week. Start reading Chapter 16 over the weekend if you don't have time during the week. On Monday, we're going to start with Chapter 16 and hit the ground running. Chapter 16 is fairly straightforward. It's not the most challenging of the carbonyl chapters, but Chapter 16 is where people start getting very, very lost. And I know some of you are going start getting because the aromatic chemistry is challenging, but we're about to start doing chemistry with carbonyl compounds. And the thing that I want you to prep yourself for is that there is chemistry with aldehydes and ketones, and then there's chemistry with carboxylic acids and their derivatives. So they do very, very different chemistry, and so you want to keep that separated in your brain. So as you start reading Chapter 16, keep in mind, like, this is aldehydes and ketones. And then when we get to, I think it's Chapter 18 or 19 is when we finally start doing carboxylic acid derivative chemistry. And that's a totally different thing. They always kind of start off the same. They share a lot of the same reagent sets, but they do very different chemistry. Anne, do you have any announcements or anything?
No, just the sessions are the same 4 days this week. There's new material now, so we'll be going over all that stuff, but that's it.
Cool. Make sure that you're going to SI. Make sure that if you're lost at all, that you're coming to office hours. We had a really fun office hour session on Monday. We actually went over like 30 minutes. I just wasn't even paying attention to the time because nobody comes to my office hours. And so people were there and I was excited and we couldn't stop. So, you know, please come to my office hours, especially if you're struggling at all. I really want to help you. Take advantage of everything that you have. Yeah, that's it. I'm gonna let you guys go. I'll see you on Friday or today, tomorrow, and Wednesday during my office hours. Do you guys have any questions?